In this video, I'm going to provide an overview of media access control. This is one of the hot areas of research in networking. There are literally thousands of research papers in this area. I myself am guilty of contributing 5 to the lot. So where are we placed right now? We have covered all the required functionality to reliably transfer data over a point-to-point link. But how useful is such a two-node network? You don't want to get stuck talking to the same person all the time. So we want to make at least a few tens of nodes talk. Our final goal is to make millions of nodes talk, that is the internet, but we will get there incrementally. But first, let's look at how to make a few tens of nodes talk. So to a person with the hammer, everything looks like a nail. So we figured out how to make two nodes talk, basically how to transfer data over a point-to-point link. So here, if we want to interconnect these bunch of nodes, just establish point-to-point links between each and every one of them. This is going to be a network administrator's nightmare. First of all, it is costly, so many links. Not only that, debugging such a network is a major pain. So we want to interconnect these nodes more efficiently. How should we do that? But before we get to that and the related problems, let me see how much you remember. So here is an outline of this video. We will first look at how to interconnect the nodes. This falls under network topology. So when many nodes share a link, one has to mediate access among the nodes. In other words, who transmits when. So in this video, we will categorize and discuss some popular media access control protocols. So this is just an overview. The actual details of the protocol I will cover when I cover the specific technology related. So here are 3 ways in which you can interconnect the nodes. The first is a bus topology where all the nodes share the bus. So for example, if this node were to send a packet, it goes over this wire and everyone is going to get a copy of it and it gets terminated here. So this topology was used in Ethernet. This is one of the earlier versions of Ethernet. Another topology is a star topology where the nodes are interconnected through a central node. So if this node wants to talk with another node, it goes through this central node. So when you use Ethernet hubs, this is how you are interconnecting your computers. So another topology is a ring where the nodes are connected in this fashion. So a packet basically goes around the ring and comes back. One important point to note here is that this shared wire or medium is broadcast. What I mean by that is when one node sends a packet, every other node that is sharing the media is going to receive this packet. That's why it is a broadcast. So this is a good place to talk about the types of transmissions. There are basically 3 types of transmissions. In unicast transmission, the packet is intended for one node only. In broadcast transmission, the packet is intended for everyone, and in multicast transmission, the packet is intended for a subset of the nodes. Note that the medium as such is broadcast, but you specify as part of the packet who it is intended for. So in terms of human analogy, for example, in a room full of people, I may say, Chotu, don't do that. Now everyone can hear this words because it is broadcast medium, but the words as such are directed to this specific person, Chotu. That is an example of unicast transmission. If I said everyone do this, that is an example of a broadcast. When many nodes share a medium, one has to address a very important problem of media access control. So if there is no media access control, if 2 or more simultaneously transmit, the packets are going to collide, leading to interference, in which case no one gets the particular packet. So the media access control is a protocol that determines how nodes share the channel, basically when a node can transmit. So something to note here is the communication about this channel sharing must use the channel itself. In other words, you can't assume that there is a separate wire to negotiate the channel access. and another wire where actually the data transmissions take place. This is not okay, just because it adds to a lot of overhead and cost. So before we solve any problem, we have to be very clear on what we intend to achieve. Like people dream about an ideal spouse, let us list out the characteristics of the ideal MAC. So if the broadcast channel has a rate R bits per second, and if there are users ranging from 1 to n, what rate should they get? So if there is only one user using the channel, what rate should he get? That's right, you want him to utilize the entire bandwidth of the channel, and thereby he should get R bits per second. Now suppose there are n users using the channel, what rate should each of them get? So it's fair that when there are m nodes wanting to transmit, each should get a rate R over m, right? Not only this, these are also useful to have. You want your media access control to be simple and easy to implement, and you also want it to be fault tolerant. In other words, if nodes fail, it shouldn't be that others cannot communicate. So to motivate media access control, let me again go with a human analogy. Suppose there is a speed dating party and there are many couples who want to talk with each other. This is not a great assumption, but let's still make it because it makes comparison with networks more straightforward. Let's assume that everyone talks loudly so everyone can hear everyone else in the room. That is what this translates to is if two speakers talk at the same time, none can understand what was talked. Now the question is, how would you facilitate meaningful conversations without any interference? So think of ways in which you can achieve this. You should come up with at least 2 techniques. It's not very difficult. So many of the media access control protocols can be categorized into 3 broad groups. This is the first such group, which is called channel partitioning protocols. In these protocols, what you do is you divide the resource into smaller pieces and allocate a piece to a node for exclusive use. So going with the human analogy, you allocate couples different time slots. For example, couple 1 can talk from 0 to 1 minute, and couple 2 can talk from 1 to 2 minutes, so on and so forth. So the name given to this type of access is called time division multiplexing. Basically, the time is divided into time frames. As you can see here, I have divided the time into time frames, and these time frames keep on repeating. A time frame itself is divided into time slots. So in this case, I have 6 time slots. Notice that I'm using the word sender. In other words, a sender is allocated a time slot, whereas in the human analogy, I said couple, which is basically a sender-receiver pair that is allocated a time slot. In networking, typically it is the sender who is allocated the resource. So this scheme prevents collision absolutely because there is no overlap across the senders, and it is also fair because each sender is being allocated a time slot in a fair fashion. But what could be the potential disadvantage with this particular scheme? So if a resource is dedicated to a user, if he uses it, great, but if he's not using it, like is in this idle slots, you are actually wasting the bandwidth. So for example, if there is only a single user, in which case he is limited to R by N, where N is the number of other users, even when all the others are idle, because you can't access their slots. So this exclusive use is not a good idea because it leads to wastage of resources. So at low loads, lot of wastage. At high loads, it's fair and people start using their slots. Another channel partitioning scheme is frequency division multiplexing. In the human analogy, this translates to moving the couples to different rooms. It's called frequency division multiplexing. So the way it is done in networks is the entire spectrum is divided into frequency bands, and each sender receiver is assigned a frequency band. Notice that I'm saying sender as well as receiver here. Here the receiver also has to tune in to the assigned frequency band, otherwise it cannot receive. So in lot of the other networking protocols, this condition doesn't arise. Only the sender is allocated the resource, but in frequency division multiplexing, both the sender and the receiver has to be assigned to the same frequency band. Assuming the bandwidth in hertz is proportional to the data rate in bits per second, if there are n senders, each sender is going to get R by n, let me call it data rate here so that there is no confusion, bits per second. Another point to note here is in the TDM scheme, when a sender transmits, all the receivers can receive that particular transmission. Whereas in FDM, a sender transmits only those receivers that are tuned into that particular frequency band can receive. This scheme suffers the same disadvantage as the TDM. In other words, if there is a single sender, he is limited to R by N even when the other senders are idle. And as I mentioned, sender-receiver channel coordination is also not very easy, because typically in networks, one sender may want to talk with many receivers at different points in time. So here is how frequency division multiplexing happens. So this is the entire frequency band, let's say 0 to 6 megahertz. So you kind of give 1 megahertz, 2 megahertz, so on and so forth.